say good evening, one and all. Welcome to the data science program conducted by IIT Guwahati. So far, we were discussing about a module called statistics, and let's quickly go through what we were discussing in the previous class. Right? So we introduced a concept called as the confidence intervals, right? Wherein we try to make sure that, right, we try to fix the interval within which we are having a specific confidence value, right? So we can, right, define the interval, right, along the PDF, wherein we can try to, right, say that, okay, I'm saying this result, right, with a specific value of confidence, right? So just try to recall the example we discussed earlier, right, wherein we will be knowing that, right, the Deepika Kumari hits the bullseye at a confidence, right? I can say that whenever she hits the arrow, 95% of the time, right, if you draw a circle around the target where it actually hits, right, 95% of the time, right, it will hit the bullseye. That will be present here. But what we did, we went behind the screen and we observed the shots over there, right? And right now you can see wherever the we were observing the marks, right? It hits. We try to draw the 10 centimeter circle. So because of the confidence we had earlier, now we could observe that the bullseye, which is the red colored dot, exists inside those circles 95% of the time, one and same, right? So if you look from the front side, you used to say that, okay, 95% of the time she used to hit it, right? Now the looking from the back side, you will say that that is the confidence level. Okay, something very much similar to the probability itself, but we don't call it as a probability, or we don't define that using any other words, but we used to call that as a confidence. Okay, so that was an example. Then we did a little bit of mathematics. Okay, so the capital P cap, right, since you are doing it repeatedly for a huge number repetitions, right, P cap becomes a normally distributed, right, random variable, and the mean is a small p, and the standard deviation is given by, right, under square root p into 1 minus p divided by n. All right, so later on we converted that into the equation number 4, right, which actually says that 95% of the time the probability that, right, bullseye is present over there in that particular circle is 95% with plus or minus 1.96 interval, because that 1.96 is the z value, right, for 95% confidence. So whatever random variable we had, which was represented by capital P cap, right, you converted that into z. So in order to have 95% of the confidence, saying that 95% of the time the P cap should lie within this region, means when you convert the P cap into the z should have a value between the two numbers, minus 1.96 and plus 1.96. Okay, so in the middle, we also have discussed that why the 0.95 corresponds to 1.96, right? Using the standard normal table, right? We could derive that as well. All right, so just try to recall that, right? Then we extended that further. Since we have no idea about the sigma of P cap, we have to go for, right, what is called as a standard error. Right? So sigma P cap is not available, but researchers already have proved that instead of sigma P cap, you can use a new term wherever you had a P, right, small letter p, replace that small letter p by P cap, right? That is also going to work in a very similar fashion with minimum amount of error, right? So the whole term is what we called as standard error. Okay, so instead of the standard deviation of the PCAP, we called that as a standard error, and we used the standard error over there. So update the formula, right? Whichever formula we had in the previous page, now we try to update that. Okay, so when we update it, what you are getting the equation that you see here. 0.95 is equal to probability that PCAP minus 1.96 SE. Previously it was sigma, now it is SE, standard error. Okay, in that range the P should lie. So going back to the classes before the previous session, right? You remember that our intention was to find out the P, small letter p, which is the fraction of the whole population. So going back to the example we considered, the P is something like what is the vote share of a particular candidate of who actually contesting a specific election, right, of a particular region, right? So we could never get into the exact P. That was because we couldn't sample and ask each and every voter of that particular constituency. Okay, but now by simply sampling, right, just 500 or 1000 people, right, with some error we can make a guess that okay, the actual P, actual vote share of a candidate can lie within a particular, within the bounds of this. What are the bounds? Right, PCAP minus 1.96 SC of PCAP should be less than or equal to P, less than or equal to PCAP plus 1.96 standard error. Okay, right. So that was a little bit of mathematics we did earlier. Then we considered an example and we said that if at all we calculated the PCAP to be equal to 0.55, considering 550 positive votes out of 1000 votes. So we guess that, okay, for this small population, this small sample, right, we got PCAP is 0.55. For the whole constituency, what should be the vote share, right? We could use the standard error first, PCAP into 1 minus PCAP divided by n. N is the total sample size which you consider, that is 1000. You see that standard error came to be 0.0157. So we wanted to have a confidence of 95%. So with the 95%, if you want to make a confidence of this, then you see that the P will be lying within 0.519 and 0.581. If out of 1000 people, 550 people said yes, we voted for him, means, right, the message is very clear. The vote share of the whole population will be 0.55 with the 3% of the error. So we could convert the standard error multiplied by 95% confidence, right? So this term is what we converted that into a percentage, right? So that is also very important, how we talk in terms of a percentage, right? So then there is another version of the same thing, right? Instead of using a confidence level, we can use 1 minus confidence. This is something like the error part or not having a confidence. So for 80%, if you say that, right, 80% is the confidence level, alpha will be 20%, the remaining part, 100 minus that 80. So if you consider in the fraction like 0.8, we have observed that the 1 minus alpha, confidence is 80%, 0.8, alpha will be 1 minus 0.8, that is equal to 0.20. So corresponding to that, we can calculate alpha by 2, half of that, and we can even calculate Z alpha by 2, which is the same term which we had used earlier. Corresponding to a confidence level, what is the Z value? Okay, so we denote that using a notation that is Z alpha. So some of the standard values used, right, in practice we have shown here. So you can see that 80% confidence means 1.28 is the Z value. 90 corresponds to 1.64, 95 corresponds to 1.96, this is the one we had used earlier in the problem, and 99% corresponds to 2.58, right? Even if we don't know this, no issues. If you have a standard normal table, we can go there, we can observe, and we can find out these values for sure. Okay, so later on we thought of how can I further improve, right, this particular result. So we have a confidence and we have alpha value with us. Using them also we can, right, we can do little bit of mathematics so that yes, considerably good answer we have. Is it possible to further increase? So in while discussing that, we understood that yes, you can improve provided you do sufficiently large number of sampling. You don't restrict to just say 1,500 or any 2,000 or any number. Randomly don't do that. Make a calculation, right? If I want to have say 5% error, 5% error corresponds to 95% of confidence. Okay, if at all I want to achieve that with that much confidence, if I want to give an answer, right, as an exit poll, what you are supposed to do, how many number of samples you need to consider, what is the total number of sample size I should collect, right, so that out of the whole population I can talk to those many people and I can get as accurate as possible result, the vote share, right? So in order to understand or in order to do that, what we did, we understood that I need to go for a specific number of samples or the sample size I need to calculate. So how to do that? What we did was the same previous equation, but we introduced a term called as the error interval. That is the half, right, interval width as the error, right? So I have a normal curve, 50%, halves of that, whatever area you calculated on the right side, call that as the error E, denote it as Z alpha by 2, same Z which we were considering that. It's the same notation is given. Okay, so that value multiplied by the p cap into 1 minus p cap by n, everything under the root. Right. That's the E equation, right, where E is the capital E denotes the error that you decide. What is the allowed error? Because I cannot say error 0. There will be error, that's a known fact. So say that I want to have an error of say 1%, that is 0.01. Which means I need to write a Z value which is corresponds to 99% confidence. Why 99? Because 1% error means 99% should be the confidence. Okay, so that Z value into root of whatever p cap you observe. You took a value, right? So this is the p cap into 1 minus p cap divided by 1, right? So that equation is there. Now we'll try to convert this into n. I want to calculate the n. So move the n to the other side, move the e to the denominator of this side, and you have an equation, right? Out of which we face a problem now, because since if at all you know the p cap, n, etc., you can calculate the n. But now that is not our idea. Our idea is that I want to calculate n here. N is unknown, right? N is what I am supposed to find out so that I can get 99%, 99%, 90%, or whatever is your decided value of confidence. In order to achieve that, what should be the number of samples that I should take, right? So in that case, I will be having no idea about what is the p cap or the p star. So what you do, take the worst condition. So recall the worst condition value I mentioned, that is 50%. So p cap is 50%, which means 1 minus p cap is also 50%. There are, right, among the number of candidates, 50% of chance, okay, to win. So a particular person winning, the chance of winning the election is assumed to be 50%. Let's assume 50% chance. Okay, so that is the worst case. Use that as the p cap. So p cap into 1 minus p cap will be 0.5 into 0.5, so 0.5 squared, divided by the error that you expect, right? You expect, say, 99% accuracy, in the sense confidence means 1% error. So there's a little bit of small maths done shown at the just last step. You can see n equal to 2.58 squared into 0.5 square divided by 0.01 square. So what's that? That is the number of samples you are supposed to, right, collect from the whole data set or the complete constituency, right, in order to guess the vote share of that particular constituency. Okay, so at least you need to talk 16,641, right, voters. So that's how we come to know about the sample size required to achieve a particular confidence level. Right. So I think I asked you also to solve for 95%, and yes, so we discussed a little bit of points about that. And then we understood that, okay, so though this says, okay, if you collect so many number of samples, you will achieve the certain amount of accuracy or specified error, right? Still, there are some aspects of sampling that still matters. You will matters you reaching closer to the P. Okay, the P cap which is calculated is closer to P, provided some conditions are set. Normally, there is a bias. We say that the sampling is expected to be biasless, right, etc. But that is impossible in a real case, right? Because of that, there will be a bias, right? Bias can be in terms of the response bias. When you ask a question, people may lie to you, right? You need to consider that, right? So somebody says that, right, I have voted, but he didn't vote at all, right? That's the second case. Or whoever participated in the voting, right, they didn't take any part in the opinion vote. They'll say that, no, I will not say. So something like that. So overall, these are the aspects which will affect the final result, that you are going to say that, okay, this is my opinion about this particular poll, right? So after that, we looked at some practical aspects. As of now, I'll move away from that. Okay, so this is what we were discussing in the previous session. Okay, then, right after that, so far that concept was related to the fraction part, right? So we have what is called as a fraction, right, which is one of the very important feature of the whole population. Whenever we want to do the statistics, right, related to a population, we have two major what you call properties to model. One is a fraction. Certain categories of problems fall under the making an estimation of the fraction, such as the vote share. Okay. The second one, which we normally have to use as a parameter when we try to solve a specific category of problem, and it is the mean, right? I need to make an estimate of the mean rather than the fraction. Okay, so one example which we have considered over here is we want to find the average height of children of certain age in a country, right? So if in India, if you want to do that, you may have to take the sample size, right? Normally we go with the smaller sample size, but practically if you want to say, I want to go accurate, means you may have to ask each and every person, right? Of that particular age. Maybe it comes in crores. Impossible task. So we cannot measure for whichever child satisfies 6 to 12 age condition. You cannot go and ask and make a note, measure that and take an average. Is impossible. What you can do, very similar. See the concept now we are going to discuss will be very similar to the fraction part we have, but the mathematical notation and the maths will change. Okay, so why we went slower on the other side? Because I wanted everyone to understand and get along with the mathematics, get along with the notations and understand the concepts, right? So we went very slow over there. Now we'll speed up. Okay, because everything is very similar, right? So it's easier actually. Okay, so let us say I will further go and take certain sample size, like maybe for whole India, if I want to do that, maybe I will try to go to every state possible, and in every different part regions of that particular state, I may collect 100, like for per state. Let me say I'll try to take 100. Okay, so overall I may get around 3,000 possibly. Okay, fine. So with that sample, right, sample size, For that sample size, I will be able to calculate the average or the mean of the height of that particular sample, right? Okay. Now we have the question coming up like we did earlier. You can say that, okay, I took a sample size and I got this value as the mean of the samples, right? How can you be sure that whatever you give as answer is going to be the average or the mean value of the complete population which falls under the particular category of 6 to 12 of the whole country, right? Because you went and you collected the samples throughout the country, you have 3,000 samples, that is fine, but how can you say that, how can you guarantee that, right? The value which you are saying as the mean or the average value, that is applicable for the whole country. So, right, you need to justify that, you need to make sure that, yes, right, I am this much confidence. You will see that the confidence is going to come at a later stage. Okay, so that is our question. Main question is that, okay, you took a sample, you got a value. Now how can you guarantee that this mean you got is the same or it is very close to the total mean of the population, right? So look at the last sentence over there. So far in the previous part or the previous property called as a fraction, we used to ask that question, right? We asked that the fraction you got for a small sample size, right? How can you say that the same fraction is applicable for the complete populations? Or how can you make sure that the population fraction is similar to the value you got for a sample fraction, right? So try to relate, things will become very easy, very simple for you. I hope, right, you're understanding what we are going to do next. All right, so let's start the process, right? So get capital D, that denotes, right, the samples, right? Collect x1, x2, x3, dot, 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 xn. That indicates that I'm collecting small letter n number of samples, correct? So everywhere I'm going to get a height, that value is x. For the first child, it is x1. Second child, I'll get a different value, x2. Third, the height, x3. Fourth child height, x4, and so on. Okay, so that is what is the sample that is denoted by capital D. Now, for this many n number of sample, you can say that n is equal to 1,000. For 1,000 children, I'm calculating the mean of the values. It's height, so mean height x bar. Okay, so denoted by x bar is equal to sum of everyone, each child's height, take a sum, divided by the number of, right, sample you consider, that is small n. All right, this is a very simple what you call very simple concept of mean. But you see, this mean is applicable only for the sample you have collected so far. I need to make sure that this sample value x bar is closer to the actual value of the mean. Okay, so this is what is the fundamental concept, right? I repeated this again and again because, right, you need to understand that what we are going to do next, right? So now we bring in a specific and very important concept that is there in the probability theory as well as the statistics. It is called as central limit theorem, right? We have used the central limit theorem in the previous sessions as well, but now I'm going, so the fundamental idea is that central limit theorem can be stated in different ways and can be applied to different scenarios as well. Okay, so the one which I'm going to use now, we have not used in this format in any of the cases we used earlier. Okay, so try to recall where and all we have used earlier. I had mentioned central limit theorem several times. Okay, but the one I'm going to use now is one of the definition of that. It says that you say that there is a population in the sense the collection of every child, right, or all children of age 6 to 12 in India. That is the population I'm talking about. Okay, so let us assume that, I don't know the values, but let's assume that that whole population has a mean value. What is the mean? that mean is denoted by this mu. You see the change in the notation now. So far, for a small sample size of 1000 children, we have calculated x bar. Okay, x bar is there ready with us. I know what is n for n number of samples which I already have collected. That is the n. So I added the heights divided by say 1000 to get this x bar. So don't get confused with that x bar, which is mean of my sample, with the mean of the whole population. So, right, population is the big number, right? So maybe it will come in crores, right? So that at the mean value of that, and let us assume that it has a standard deviation of sigma. As of now, I don't know. Okay. If at all you have a population of mean values mu and standard deviation sigma, then, right, it's a statement directly taken from the central limit theorem, right? We don't have to prove it. It's a well-known fact. Then any smaller sample you collect from that bigger population, right, that is going to have a mean x bar that is always normal distributed, okay, with the same value of mu like your complete population. Whatever is the mean you have for the complete population, the same mean will be available for this. They have proved it in the central limit theorem. And the standard deviation of your population, that is this not population, my mistake, the samples. Okay, so the samples will have a standard deviation sigma by root n, right? In the sense, I have so many samples over here, right? If at all I take the mean of that mean, right, is something like this, and the standard deviation of those samples will be sigma by root n, where n is the number, the size of the samples, and sigma will be the same standard deviation of your whole population. So now things become very easy and very clear for us why we applied the central limit theorem. So I think in the previous sessions, whenever we use the central limit theorem, we use the fact that as n increases, right, any particular distribution will tend to become a normal case. So it's actually, in another way, we are talking about the same concept now. So population means it is definitely larger size. If at all you have a population of mean mu and standard deviation sigma, the x bar which you have calculated, the sample mean, is also going to be a normal distribution with the mean value mu and standard deviation sigma by root n. Okay, directly collected from, right, the central limit theorem. Okay, fine. So now, how can we use this in our problem, right? So in our problem, we are going to use it in the following fashion. So see the message written below. Irrespective of the shape of the fx of x. What is fx of x? It's a PDF. It's the distribution, right? Now, when I said I mentioned that if the size is too large, it will follow the right normal distribution like this. But it is not necessary. It says that irrespective of the shape of the fx of x. It means it can be even exponentially, it can be even exponentially decaying. This function is also fine. But you are going to have some mean and some standard deviation for that, right? That itself is denoted by mu and the sigma. That is for the whole population. Population may follow any of the distribution you know. Doesn't matter. Irrespective of that, I need to know only what is the mean and the standard deviation of that. Okay, that mean and that standard deviation I can use, and I can actually represent this. That is for the x bar which I have calculated. I can make sure that the mean of that x bar is mu, same mu as the previous one. Okay, like the whole population, and the standard deviation is sigma by root n. Okay, so that means the distribution of the mean of your samples, right, is going to be governed by, in the sense that mean will be somewhere in the surroundings of the sigma value, and the deviation from the sigma will be denoted by the actual sigma by root n. Is that clear? Do you have any doubt? Yeah, we are open for questions. Let me clear your doubts and we'll proceed further. Okay, any doubt with the notation X bar, and we use the word X bar distribution, right? Anything related to that? Yeah, yes, Ruchi. Hmm. No, population size is not being considered in any of the cases so far. Whatever n we have written, that corresponds to the size of your samples. Okay, 1000 samples if I have considered, then the X bar, that is the mean of your sample, right, is going to vary. It's going to follow the normal distribution with the same mean of your population, that is mu, but with a different standard deviation sigma by root n. So where n is the number, that's 1000, 2000, 5000, 100, whatever you choose as the sample size. Yes. So similar question, I think I tried to answer in one of the previous class as well. So just think that I collect 1000 samples, okay, and I will calculate the mean of those 1000 samples. Okay, so that is denoted by the sample mean. You look at this, right? So sample mean means it's the mean I obtain for the samples. Okay, 1000 samples I collected, whatever is the mean, that is X bar. So equation is also should be very clear to you. Okay, take the height of every 1000. So I got a reading of 1000 children's height. So sum of them divided by 1000. If that's what is we are denoting as X bar. But you see, the population mean is mu, in the sense in the country there may be 1 crore, 2 crore, maybe whatever. So many children satisfying this condition, right? Whose age between 6 to 12. There, right? It's a mean of everyone considered together. That is the population. So that has to be a different value, right? That is denoted by mu. Okay. So now, huh, yes. So our idea is that using the X bar, I should be able to go as much closer as possible to the mu. Correct? Is that right? Yes. So relate this to the previous case where we had a fraction from one population. Our intention was to use that P cap to reach P. So P cap is not there now. We have X bar. So P was the mean. Now we have mu over. Okay. So relate them. It becomes easy for you. All right. Yes. Mu. But I cannot do that directly because I have to talk to 1 crore, 2 crore people. Yes. So I can do what I can do best is calculate X bar properly and then use that somehow to reach the mu value. All right. Yes. Any other doubt? Okay. So central limit theorem comes in handy over here. We use what we require from the central limit theorem. Again, different authors and different references state the central limit theorem in different ways, but right, any one format, each one of them will be used for various kinds of applications, right? So the one which we require, we have used. Okay, fine. Now, so the idea is that I got X bar. Okay, for X bar, right? You recall what we did. We actually collected 500 samples initially. We calculated a fraction, then repeated the experiment once again in a different location, right? So that's what we did earlier, right? When we were dealing with the fraction. Now we repeat the same thing. So I calculated the height of 100 children in a location. I move to the other location and I calculate one more 1000. Let's say. So I will note that my X bar changes, isn't it? So X bar will definitely change because, right, depending upon the physical, so the geographical location has something to do with the physical fitness as well, right? So right? We know that that's a well-known fact. So because of those parameters, right, height will definitely, so average height of children will definitely change, right? So because of that, small change will come into picture. So X bar will vary when you move from one geographical location to other geographical location. Okay, so X bar changes, and every time I conduct this experiment again and again, I calculate the average. This X bar slightly moves, right? You may get say 110 centimeters, next 115, then you may get 95, then you get 135, maybe there is a variation. Let's see. Okay, so you understand that this actually follows, as you increase this number of repetition, this will follow a normal distribution, right? Again, I am taking the other version of the central limit theorem. Okay, so it follows something, right? You know that shape. So what you do, normalize your X bar, right? What you do, normalization means the last equation, Z is equal to X bar minus mu. Now I'm not dividing by sigma, because sigma is the standard deviation of the complete population. That I cannot use, because I'm trying to model or normalize only the X bar, which means I should use the standard deviation of X bar. So what is that? That is, you see the difference. So I told slightly mathematics will differ from what we already have discussed, but the concept remains same. Okay, so look at the equation that we have here, right? That relates to the standardization of the X bar into Z, the conversion into the Z, right? You can call it even as a Z transform. Okay, so Z is equal to X bar minus mu divided by sigma by root n. Okay, once again, I'm opening the question session, right? Do you have any doubt with this equation? Right, I'm talking about the normalized random variable, the last equation on this slide. If you have any doubt, yeah, please ask. Okay, so that's good. So I hope you are understanding the concept, right? Just try to relate. Now, what are the issues, right? In order to calculate that particular sigma, right? Sigma by root n, which is there in the denominator, I need to know the sigma, correct? Isn't it? So I can ask one question here itself, right? What are the problems associated with this equation? Anyway, you told that you understood this equation. That is fine. But my question is that, what's the catch? Can you substitute every value in this equation and get the Z, right? Is it possible? Can you use this as it is? Okay, so mu is the mean, right? Two answers I have. The first thing is that this mu, look at the central limit theorem's usage. It says the mean of your X bar is same as the mean of, right, this mu. So population mu and this mu are same. That's one thing. Okay, I can deal with that. So whatever is the mean you get for X bar, you can substitute. It's not a problem. The first point. And the second point is that, anyway, you are normalizing means mean will come to the center. Mean will become 0 when you do the normalization. So I think that's not a problem. What's the other thing you were supposed to say? What's the next part? Anyway, you told that mu is unknown. Okay, I accept it. What's the other part? Do you know every other parameter over there? Right, for the whole population, whatever is the sigma, we don't know that. That's actually a major problem. Okay, mu you can deal, right? Because, right, after taking certain you repeat the experiment several times, right, you will be coming closer to the mu. That's actually not an issue, because the same mu is available even for the total population. Whatever mean you calculate for X bar, right, that will be the mean of that. So that, your answer is right. I don't know two things. One is mu, one is sigma. Out of which I am saying mu is not a problem. Okay, but sigma is not known means this whole equation, right, is of no use to you, right? So that is actually our problem. So you see issues. One is that n should be larger. That's what we are expecting, so that I can apply this equation, because equation assumes the normal distribution. For that, you need to go for a larger size. First thing, let us say that yes, we did that somehow, but in order to do that, I need the complete, right, sigma, right? Only when that is known, you can do. Okay, so what we did in the fraction, you recall and give me an answer. What is your solution? Anyway, remedy is there, but don't look at this. Try to recall what we had done earlier, and I'm expecting that answer. So we didn't know something over there. The sigma of p cap was not known. Correct? What you did, try to do the same thing over here. Okay, is my suggestion. Yeah. Okay, anybody who can guess and answer that question? Yeah, please go ahead. That is the value of p cap. Okay, what you are saying is p cap. Now our intention is not to put a value of p cap. I want the sigma of p cap, something similar to that. What was the standard deviation of p cap? I didn't know that, so I did something. Okay, so what you did over there, you can do the same thing here. As of now, I don't want the value of p cap. If at all I wanted something similar to p cap, yes, your answer would have been the correct one. Okay, I'll put 0.5. But as of now, that is not my intention. Okay, yeah. Multiplying both sides by standard deviation. I think that was in a different step, right? Okay, so just let me go back. Right, I didn't know what is called as the sigma p cap, right? So you see this sigma p cap, I don't know, right? In this equation, sigma p cap, I don't know what to do, right? So you see here, I don't know the sigma value. I brought up a concept called as standard error, correct? In the sigma p cap, you go for the standard error of p cap. Are you able to recall this? Yes. Okay, so let's do a similar thing now. Right, so this is my equation, right? I want to go to this, right? I want to actually perform this, but in that I don't know the denominator, right? So what you do, instead of calculating the sigma, right, you replace that with what we call as s. Okay, that is the standard deviation of the sample. I don't know, that it definitely brings an error, right? So I wanted to put the sigma there, which corresponds to the total population, which I don't know. What I know is that I can calculate for a given sample of 1000, right? Definitely I can calculate the sigma of that. That I don't write it as a sigma, but I write it as a s. A different notation, that's all. Okay, so there it is se, here it becomes s, right? So just see here, right? I needed a sigma. I don't have a sigma. I will put s in position of sigma. So sigma by root n I replace by s, where this is the sample's standard deviation. I can definitely calculate. And the standard deviation of 1000 children, I can calculate because I have that, right? Are you okay? Same thing we did earlier. I'm doing this. I'm going faster. That's all. I'm not doing all the maths behind that. So that's one thing. So whenever you replace the sigma by s, you are not going to get the z on the other side. You get something different. We call that as a t. Okay, it changes. Let us say that my horizontal axis is a t. Okay, so since you are using the samples standard deviation instead of the actual sigma required, which is the sigma or the standard deviation of the total population, right? There is some error. Okay, but still, again, this has been proved. I'm not going to prove that. Not going to do any maths right now. Okay, so again, this is a very well-known fact, and even this is a standard distribution. We never consider that, but now onwards we are going to discuss about this as well in detail at a later stage. So this is known as the T distribution. So you have heard of T distribution. Specifically, this is called as student T distribution. Okay, so now you see, right? By just replacing the sigma of the whole population by the sigma of the samples, we jump from standard normal distribution to a new distribution which is called as student T distribution. Okay, so see the equation here, no change. Only the difference you see is that x bar minus mu as it is, right? Divided by, instead of writing a sigma there, I write s by root n, where s is the sample's standard deviation and n is the number of sample you consider. So definitely this changes with n. What's your opinion? What happens when I decrease n? What happens when I increase n? What happens to the value of t? Anybody? If I decrease the value of n, what happens to the value of t? T is something similar to Z, okay? Yeah. Yeah, when you reduce n, t will reduce. When you increase n, t will increase. Perfect? Yes, that's right. So it is directly dependent on the sample size. So why it is dependent on sample size? Answer is present once again in the same central limit theorem. It says that increase the what you call n, it follows the standard right curve. So as the population size increases, this is what is going to happen ultimately. Okay, so they already have, they told that in the statement of the central limit theorem itself. Okay, so right, if you have any doubt with this equation, yeah, please go ahead, otherwise I will go. Right, let's think about what all the things we discussed in today's session, right? And right, if you are okay with this equation, yes, I'll go ahead. All right, so that's good. Let me move ahead. Right, now related to the fraction, right? Yeah, yes, go. Sure. Hmm, hmm. Okay. Uh, as of now, if you want to go back, yes, you can go back, because just modify the equation, it gets changed, right? We had x bar, I converted x bar into t. Okay, if you want to go back, what you are supposed to do, the s by root n will be moving to the left side. So s by root n multiply by t, the mu which is there, you take it to the other side, so x bar comes back. Okay, that's how, if at all you want, you can go back. Okay, but according to me, no going back is required, because here itself I'm going to get my answer, right? My answer is, how can you convert x bar into mu, right? That was that was my question. Sorry, x bar coming closer to the overall mean is what my question, right? I'm able to solve that here. Okay, so going back is not required, but if at all you think that yes, I have to go back, this is the solution. Yeah, we have something coming. Okay, so maybe 1 or 2 slides, I'll try to come to a solution, then we'll solve the problem. All right, fine. Okay, so I hope everything is clear so far. That's good. Let's proceed. So now recall, we brought the idea of confidence level, and corresponding to confidence level, I have to have an interval. So look at the graph which is there, right, over here. So this is corresponding to the plot of t for different values of n. Okay, so look at the one which I'm highlighting now. This is the one with the smallest value of n. Okay, so the red colored one which you see, right? That corresponds to the small sample size. When n is very small, it looks like a different graph. It may not be the standard normal graph. This still follow in some sense a normal graph, but it is not standard because it may have the mean equal to 0, but the standard deviation, the range is not 1. Okay, so that's the point. That's because of that, right? Whenever you go with a very small sample size, this is the curve, right, that we get. Slightly increase, go to a slightly larger, right? So the slightly larger one is the intermediate graph. You see something goes like this, and it comes down. Okay, so the middle graph, right? That is not going to reach the exact peak, and that is not the lowest one. It's somewhere in the middle, you see that. That is for a larger sample size. Okay, if you increase this larger size to further, right? Go to whatever highest number possible. Not in just hundreds. Maybe go to thousands or more than that. Beyond that, that will tend to be a standard normal curve, which is the highest peak, with the curve which reaches the highest peak, right? So that is this curve. You see that goes to the peak and then comes back. So that is the standard normal curve. Again, I tried to replicate the statement of the central limit theorem once again. I had some distribution. You try to plot the same distribution with increased number of samples, right? So the distribution automatically tends to become what is called as the standard normal curve, right? So I want to use this concept now. So far what we discussed, I'll try to highlight that once again. So the total whole population has mu as a mean, sigma as the standard deviation. I collected samples. I say that x bar is the random variable of the mean corresponding to the mean of my sample size. That varies when I repeat the experiment, right? According to the theorem, it is going to have a mean mu and the standard deviation denoted by sigma. I don't have a sigma, so I replace that by s. So I will call that as the standard error of x bar. So previously standard error of p cap, now the standard error of x bar. Equations are different. There you used p cap into 1 minus p cap by n under root. Now I don't have to go to that. I can use the standard deviation of the sample s divided by root n. This is the one which I am supposed to use. So wherever you use p cap into 1 minus p cap by by n whole under root, don't do that. Do this now. Whenever our intention is to look at what is called as the mean and its distribution. Okay, so that's very important. Now I have to go to the t variable. It normally referred as the statistic. Statistic of t means this is the equation. Okay, so x bar minus mu divided by the standard error of x bar. So how this is going to be plotted, I have shown. If you have a smaller value of the sample size, you get the smaller graph which has lesser height. But as you keep increasing the sample size, you can see that that tends to be a standard normal. Why we are highlighting, why we are stressing the standard normal is we are very familiar with that. We know the complete mathematics of that. That is easier to understand, easier to analyze, and everything is readily available, right? So that's why everything we try to relate to that. Is it okay? I hope things are getting more and more clear now. Yeah, please ask if you have any question so far. Yes. Yes, we simply say that replace the s by root n, call it as a standard error of this. Okay, you don't have to write. So previously also we did the same thing. Instead of everywhere writing root of p into 1 minus p by n, sorry, p cap into 1 minus p cap divided by n, we simply called that whole term as SE of p cap. Correct? Same thing here. Okay, sure. All right, so let us proceed further. Right now, right, here also corresponding to an alpha, a specific level of confidence, we have several values corresponding to the t distribution. What this t value will take. What value this t takes is called as a t distribution. Like the standard normal distribution table, we also have a t distribution table. Okay, again, I have not shown the complete table, right? But whatever I am showing here is enough to understand the complete big picture. Okay, so you can search in the t table in the Google, you will get that. Okay, so I don't want to go to that level. Anyway, whatever I have, I will even solve a complete problem using this. Okay, so for a t distribution, it's not a normal distribution. Just understand, we cannot go to the normal distribution table to solve. That is possible only when you have sufficiently large number of samples. Let me say normal. Now I am going to discuss a problem where you will understand that why it is always not possible to go to a larger size of sample. I will make a statement now. I say that it is always not possible to take a larger sample. Sample size sorry. So the sample size is always most of the practical problems will be right just maybe 10, maybe 5, maybe right 15 at most. Now when I said the initial statement of my problem, I said that I wanted to calculate the height of children of certain age. There no issues, you can go and you can calculate. You have time, money, yes, definitely no issues with that. But the one problem which I'm going to solve now, you will understand that it is impossible. It is impossible to go beyond 5, 6 or 10, right? I have such an example with you. Okay, I'm going to come to that. So normally the t distribution you are going to apply, right, with lesser number of samples only. Sample size is not going to be a larger number. So generally we said that, okay, increase n, your curve becomes normal, everything is standard, you can solve easily. Yes, everything is true, but practical sense is completely different. That's a theoretical aspect. So doing mathematics and proving that, okay, this follows the central limit theorem, etc., is practical, is not going to happen in a practical scenario. Okay, so what we are showing here is, right, so what you see here is the sample size. So sample size is said to be, there is another name technically, so I wanted to bring the name here, so that's why I exactly copied that, right, from a website. It's called as a degrees of freedom, right? Degrees of freedom, in the sense that that's another word used for your sample size. So I also have denoted that over here, right? If you see the what is called as the degrees of freedom in any of the references, don't get confused, they are simply referring to the sample size. Okay, first, now I have a mean, say mean is 0, the student t distribution I have, it's not a normal distribution, some other distribution, okay, some other shape. Along that distribution, right, since you have performed x bar minus mu, it will shift to 0, no problem with that. But you see, it is not going to have a sigma value equal to 1, right? It is something else, correct? So because of that, right, the value you used to get for a z is different. So it's no more z, it's a t, but you don't get the previous value. Like for 95%, we actually have, right, we mentioned that was 1.96, irrespective of your sample size, that is a fixed one, right, in case of a fraction. Okay, so make things very clear now. Okay, but now it is a different distribution, and your sigma and the sigma is completely different. For the population it is different, for the sample it is different. So because of that, depending on what is your degree of freedom, or depending on what is the sample size you are considering, the t value changes. For example, I'll just give a simple example. Let me say my sample size is just 1. Okay, sample size is 1. If you want to have a 90% confidence, right? If you want to have a 90% confidence, the value of t is 6.3. Very easy to read the table, right? Similar table which we had considered earlier, there we had the z value, I have the t value. So recall, you had only one row here. Okay, this was a single row. Z alpha by 2 was a single row, because you didn't have to worry what is the sample size. Irrespective of the sample size, you have the same Z alpha by 2. Clear? I hope, right? No doubt here. Okay, let's proceed. Now I change the sample size or degrees of freedom to 10. Instead of taking one sample, I take 10 samples. Yes, Upkar. Yes. Only one. I ask the height of only one child. One. Okay. When I say 10, I ask 10 different children. What's your height? What's your height? What's your height? And I do them. So that is 10. Okay. Yes. So going further, if I consider 10 heights of 10 different children, for 90% confidence, right, you have to use just 1.81. See, when I had 1, the t value is different. When I have 10, the t value is different. Go further. Take 100 samples. For 90%, your value is equal to 1.66. Correct? So as you increase, this is what I mentioned earlier. As you increase the n, the t value is going to vary in a similar fashion. Right? So for 95%, consider this is very standard, right? So let's go to the 1.95. Sorry, 0.95. My mistake. So when degrees of freedom equal to 1, you are supposed to write 12.71. Change this to 10, it becomes 2.23. 30, it is equal to 2.04. 100, it becomes 1.98. At infinity, this becomes equal to 1.96. Yeah, yes, Ruchi, yes, Ruchi. Sorry. Here we are calculating the probability, okay, not the exact t value. Okay, so don't relate the t value here, not the exact value, that's the probability under that we are calculating. Okay, under the curve, area under the curve is represented here. Okay, all right. So just see, right, that's right, it changes in this particular fashion, right? So the idea is that the value is going to change, that depends upon the degrees of freedom. Right? So larger the sample, right, the value tends to reach, right, the standard norm. Is it okay? Right. Now, yeah. Okay. So the actual problem comes into picture. Say the question I want to form here is this. Several car manufacturers wants to estimate, right, the average repair cost of a car, right? So how do you come to know that the average cost of this, right? You need to do a crash test, right? Now you see how many samples you can get. Whatever they manufacture, they cannot bring it into the crash test and do that, right? Right? So it's impossible. So limited, very limited, like 5 cars, maybe 10 cars, like they may do that. So this is the question. We'll try to solve this now. Okay. So the question is, after crashing 5 different cars of a company, right, the repair cost came to be 15,000 for the first car, second car, third and fourth and the fifth. All right. So now the question is, estimate the mean of the whole population. They have manufactured so many number of cars. If all the cars will go to, say, a repair, what is the average? Right? So understand that I will never get a large number of samples over here. Okay, so the question is clear? Yes. Okay, so I'll move on to the pad and we'll solve the problem. Okay, so just bear with me. All right. Okay, if you want to see this, I'll show the question once again. Those who want to make a note of those values, quickly make a note. Okay, I'll give say 30 seconds for that. Right? See the values. 5 cars we have. The values are 15,000, 40,000, 72,000, 50,000, and 93,000. Okay, just note a value. So the question is, with 95% confidence, you should calculate the mean. So whatever mean value you get, you should give a range. Okay, the repair cost in average comes between this number to this number, like we predicted the p value in the fractional case of problem. Is that fine? I hope everyone have noted down this. Table, don't worry. Okay, I'll bring the table back whenever required. Okay. Right. So what I want to do, I'll start from this part. So yeah, sorry, I'll change the screen first. Just a second. Okay, all right. Right. So what is the equation for the mean? Right? Try to recall. Right? The mean is calculated in this fashion. So just a second. Sorry. The mean equation is mu is equal to the x bar is a sample, right, of mean of your sample. Okay, plus or minus, right? Now 95%. Okay, so 95% means I need the table. Okay, I hope, let me check whether I can bring the table here. Just a second. Yeah, so I think I can bring the table now. I'll bring the table and I'll paste the table to this page itself so that we can refer. Okay, just give me 1 second. Yeah. I'll bring it so that everybody can refer. Yeah, okay, that's right. I'll copy and paste the complete table over here. Okay, so yeah, what's the answer you are saying? 2.57, right? So okay, it looks like our table has no 5, right? 2.57, it's there. Okay, let me just check. I think I'm seeing a different one. Let me quickly. Yeah, we have 5, isn't it? Okay, that the one which I'm seeing was different. Sorry, I'll quickly copy the one which we are seeing. All right. Yeah, I'll slightly zoom this. Okay, so what I'm supposed to do here is the value that I'm considering it as a t value that I'm supposed to write over there. Correct? So that will be the t value correct from the table. So we can see that, right? If the value that we are going to consider is right, like 5, what is that? That is equal to 2.57, right? So let's see that. That is this value, because 95% and degrees of freedom being 5. So that this value should be, right? What value I am supposed to write here? 2.57, isn't it? 2.57 is the value. And right, other than that, what you can write, multiply that with, yeah, what value you are going to write? Yeah, so let me write an equation. Yes, your answer is right. I am supposed to do SE of X bar, right? So this is the equation which I am going to use. Okay, now I don't have those values. I am supposed to calculate, right? So X bar means it is the mean value of, right, the cost of each individual car. Okay, whenever you crash test and try to repair that car, whatever is the cost. So let me write the X bar over here. So sorry. So let's do the calculation. So X bar, what are the various values you have? I think 15,000, the first number. Then the second one was 40,000, right? Then 72, right? Okay. Later on, yeah, 50,000 and 93,000, right? So take the sum of them because I want to take the average, right? So first you take the sum. So what is this? I'll just write this is summation of X bar. Okay, please do the match and give me the answer. It's a mean. Okay, so can you give me the sum here? Later on, I'll convert that into the mean. Okay. Okay. This is the sum. So the mean of X bar, right? I'll write, right? So that mean of X bar should be 54. Okay. So, right. Okay. Let me write a X bar itself. So that itself is a 54, right? Correct. Right, so this is not X bar, sorry, that's my mistake. So I'll simply write the heading as a cost. Okay, so the next thing is that, right, it can be simply X. That's all. Cost of every car is X. Next, I need, how do you calculate the standard deviation? Do you remember an equation for that? But S is required, right? S is equal to, S is what? S is the standard deviation I need to calculate for this sample of 5 cars. So how do you do that? You need the square of every term. Okay, so if I call this is X, I need X squared. Okay, so cost is denoted by X. I need X squared. Right? So please calculate that. So this is 15,000 squared. You can even write into 10 to the power. No problem for me. Okay. So 15 into 15 is 225 into 1000 square is 10 to the 6. All right. Like that, you can give a notation. That's easier to write instead of writing 6 zeros, right? Write it something like this. So second one should be 4 into 4, that is 16. So there is 4 zeros, so that becomes 10 to the power 8. Or you can even make it into the common 10 to the 6 everywhere by making it as 1600. Okay, 1600 into 10 to the 6. Anything, whatever you prefer, you do that. No issues. Okay, I ultimately need a sum at the end. Okay, right. So keep filling. So I'll write what's the next number? 72. 72 square is I think 5184 into 10 to the, I'm not very sure. 2 into 2, 4. Yeah, it's correct, right? So power 6, right? Okay. Then I can write 25 into 10 to the 8, I guess. Then I can write 93. 3 is 9, 8, 649. Okay, into 10 to the same 6. Okay, right. So yeah, so better to write in that way. Okay, 2500 into 10 to the 6 because you can get a common 10 to the 6 here. Okay, so please someone give me this answer in 10 to the 6 order. Okay, don't write 10 to the 8, 10 to the 6. 225 plus 1600. Yeah, yeah. 1800. 18158, correct? Into 10 to the 6. Okay, fantastic. Now, again, this is actually the sum of X square. right? So what we have to do here, right? You need to calculate the average of this. Okay, so I will write that. Okay, so this is x bar. So calculate the average of this number. Okay, so divide this by 5. Okay, so divide this number by 5. Okay, we can call that as the expectation of x squared. Yeah, what's the answer? 3631.6 into 10 to the 6. Okay, yes, let's take that. So others please verify. Okay, so if there is a huge difference, please tell. Okay, otherwise I think we can go with this. Okay, now the S square, which is the variance of this sample, the 5 cars which have been crash tested, right? So their what you call as the variance is S square. Okay, S is the standard deviation. You can obtain that by taking the square root. But we don't have a direct equation. We have an equation for S square. So try to recall. If you have studied probability somewhere, you will be knowing this. If you don't know, don't worry. Just apply this equation. We'll come to that when we deal with the probability. Okay. So this is the equation. The equation is the expectation of x square minus the expectation of x the whole square, right? So this is the one which we are talking about. This is the expectation of x. Okay, expectation of x square is already there. So right, we need to write this. So that is equal to 3631.6 into 10 to the 6 minus 54,000 square. All right, yeah, so please do this. We get the S square, which is the variance. Yeah, you need to add these column to get that answer. Okay, sure. Okay, I just added a step so that when you refer to this, you will understand. Okay, so fine. Take your time, no problem. Calculate S square. Okay, so we have an answer. So S square comes to be 715.6 into 10 to the 6. Okay, so others please verify this answer. Yeah, same thing. Oh, that's good. Fantastic. So S is required, which means you need to take the square root. Okay, so 715.6 into 10 to the 6, that will be the standard deviation of the 5 samples which we have collected. Okay, so how much? 26.75 into what's the power you are getting? 26.75. May not be 10 to the 6 because 10 to the 6 is under root, right? So I am expecting into 10 to the 3. All right, just verify. Okay, so S comes to be, right, 26.75 into 10 to the 3. Okay, so 26,750. So this is the S value. Everyone getting the same answer, or do you have any difference? Okay, all right, all right. So S comes to be this value, right? So once we have the X value, what do you expect? I think we have everything required, right? So go back to the equation, check the equation that we are supposed to use, right? So the equation says mu is equal to X bar plus or minus 2.57 into SE of X bar. So I'll use that. So therefore, the average repairing cost mu is equal to, right? It is the X bar. X bar is nothing but E of X, which is 54,000. Okay, plus or minus, right? 2.57 into standard error is what is required. That is S divided by root n. Correct. So what is S? 26,750. Okay, divide by root n. N is 5. We used 5 cars. So root 5. Okay. Now you see, because of the plus minus, I'll get two answers. When I do plus, I get a bigger number. When I do the minus, I'll get a lower number. See, that is what is the range we were expecting. Okay. Yeah. Please do the calculation and tell me the minimum and the maximum value you get. It comes in thousands. Okay. 54,000 plus some thousands, you get a bigger number. 54,000 minus some thousands, you will get a smaller number. 2.57, it is directly collected from the table. Okay, so just see this table. I have marked with the red color, right? So for 5 cars being tested on the left side, on the top I can see 95% confidence. That's what was mentioned in the question. Okay, find out the mean repairing cost of a car, right, considering these 5 crash test results, right, with 95% confidence. All right, yeah. Okay, yeah. Yeah, kindly repeat once. I couldn't hear you. Okay, so what's the first answer? Yeah, what's this? Smaller number? Huh. 171.5. I think there is a different answer by Ruchi. Okay, everyone please verify. Okay, you should get the appropriately small answer. Okay, from there to 828.47. Okay, compare your answer with the Ruchi. Okay, once because there's a different answer over there. Okay, let's wait for others. So the indication is that the average repairing cost of a car can be between 23,000 to say 85,000, right? That's what is the conclusion of the car manufacturer. So by just doing 5 car crash tests, they'll come to know about this. So this is the idea. You will never get to see a huge sample size in practical scenarios like this. Okay, so it's impossible to crash every car you manufacture, right? So doing that test is impossible. So because of that, we have this restriction. Under such condition, the T distribution is going to come in handy to make an estimation. Okay, like this. Okay, so okay, so I'll update that. Okay, so the same answer I'll write. Okay, so that is 23255.19, starting from this to 847744.8. Okay, 0.8. So anywhere in the middle you can have the average repairing cost of the vehicle. Okay, so do we have any doubt? Please let me know. Otherwise, we'll go for a tea break. So with the same data set, I want you to solve, right? I'll modify the question. That's all. Okay, so we have the same data set for the same cost of repairs of 5 different cars, right? Repeat the problem for, let me say 90%. Okay, 90% confidence. Right? What happens with the 90% confidence is my question. So you don't have to calculate again the E of x and E of x square. They are already available. Only the multiplier with which you multiply things. Okay, so right. So for 5 vehicles, right, data size being 5 and 90%, you are supposed to use 2.01. Okay, so that's how you do the calculation. So just give me the answer directly, right? What is the average cost of repair of a car if you consider 90% confidence? So I'll just note down the number is 2.01 and use that in this case. So this position will be changed by 2.01. Mu becomes equal to 54,000 plus or minus 2.01 into 26,750 divided by root 1. Okay, so we have an answer. So that is 29,954.45 to, this is 78,045 point. Yeah, so we have one answer 0.1, 0.5. Okay, just verify whichever is closer, you write that. Okay. Okay, I'll give 1 minute of time for everyone to finish. Okay, any doubt with this? The way we do the calculation or anything related to this, the alpha and the t distribution and the calculation of the mean value of the population, right? The range with certain confidence. Okay, so in that concept, if there is any doubt, I would like to clear that now. Yes, Manish. Yes, definitely. Please. Yeah, please go ahead. This one. That is because percentage, the confidence level changed, right? So according to the confidence level, you need to refer the table and change your t value. Okay, so just look at this. I'll show that again. So see, right? So I actually change the color, right? For 90%, look at the green color, right? So 90% it is 2.01. Okay, 95 it is different. Okay, no issues, absolutely fine. That's fine. All right. Okay, so right. Any other doubt? All right. So another question, right? Uh, right. Just one second. The pen is not being detected. Just sorry for the inconvenience. Just one second. I'll just reboot. Okay. The repair cost of 10 different mobile phones, okay, uh, are found to be 2,800, 3,750, 1,985, 6,675, 4,800, 9,250, 7,780, okay, 9,180, 5,400, and 3,650 rupees. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, we have 10. Right? Calculate. Calculate the average repair cost with 99% confidence. Okay, so for which I think you need a different table which actually shows you up to 10, right? So what I do, I'll paste another table below this question. So meanwhile, you please note down the question and I'll try to bring up the other table. So note down the values, okay? And meanwhile, I'll paste the value. Okay, values visible, I guess, right? On the screen. May not be the whole question, but still the values are visible. I guess. So I'm expecting people to use this particular table. So just hold on. Okay, so supposed to use this table. Right? So follow the same procedure like previously. First, I am expecting the following values, right? One, I will not do the complete table, right? Do the maths, right? And give me these answers. Okay. The first answer I'm expecting is the E of X, right? So that is a X bar in the table. So take a sum and divide by 10. Then another column where you square every number and take a sum, and from that, right, you will try to calculate what is called as E, expectation of the X squared. Okay, so we have one answer, 55,270, right? So divide by 10, I think E of X is that, right? So yeah, so Ruchi is also saying the same thing. So I'll write that answer, 5527. All right, yeah, please go ahead. Yeah, definitely, definitely. Just 1 second. Yeah, okay, this is the complete question. Okay, so we have one answer for E of X squared, right? Let me write that down. Meanwhile, I expect others to verify that. Okay, so this is 3, 6, 6, 2, 8, 4, 1, 5. Previous problem? You mean the previous one? Okay, okay. All right. So you mean this one, right? Okay, this is the one. Okay, mu equal to x bar. There the problem begins. Okay. Sure. Okay. All right. Okay. So the next thing we are expecting is the s square. Okay. So go ahead and calculate the s square values. Okay, so the one answer which we are getting now from Ruchi is 66080 686. Okay, others please verify this answer. So from s square, you take a square root to get the s, that is the standard deviation of the given data set. Okay, so that is 22465.90. All right. So the mean value you are going to calculate now using the formula, that is x bar, that is nothing but expectation of x, that is I think 5527 plus or minus 10 with the 99%, right? So this has to be 4.14, okay, into the s value, that is 2465.90 divided by root of the number of samples. You can see that that is 10 here. All right, so verify the answer. Average cost is 2298.71 to 8755.29. Okay, so others please verify this answer and let me know if there is a major difference compared to this. All right, I'll give 1 minute for everyone to finish, right? Then we'll proceed further. Okay, others, what answer do you get? Same answer, or is there any difference? Anybody who one more answer I'm expecting. If it's same, then fine. If it's different, then we'll verify that answer. Okay. Anybody? All right. So let's go back. So we have solved the problem using which we will be calculating the average, right, of certain population. Yeah, I think we have one of the answer matching, right? So Somesh says that minimum values remain same. Okay, so please calculate the upper value, upper cutoff value, and please paste it over there. Okay, Somesh, I'll see that. So meanwhile, let's move ahead, right? So I hope you are comfortable with this kind of calculation, right? So the next thing is another quiz. All right, so everybody, please look at this and try to answer. All right, so I'll try to create a quiz for you. Right? It's not creating. Okay, yeah. Please paste your answers like you did earlier. Okay, it's not creating the poll as of now for me. There is some issue with the back end of Zoom, I guess. Okay, so you don't have to type the complete answer. Just write 1A, 1B, 1C, depending on your answer. Like similarly, 2A, 2B, 2C, just write that. Okay, 3A, 3B, 3C, 3. Just type that. I think that should be sufficient just for me to understand uh, how much you are catching whatever we are discussing today. All right. I'll give total 2 minutes. Right. So just think and try to catch whatever, try to recall, right, what we were discussing so far, and try to answer this. Okay, I'll give 1 more minute. So whoever did not answer, right, please try to answer within the next 30 seconds. All right. So let us try to discuss the answer here. So for the first question, all right, what is the sampling distribution for small sample mean? Right? Whenever it's a small sample and you are trying to find out the mean, right, of the total population, it has to be the student t because it's a mean, right? Mean means it's a continuous variable, so it cannot be, right, a distribution which is discrete, right? So that means may not be two of them. Normal will come into picture only when, right, when the sample size is large. So that means the possible answer here is the student T. Okay, yes, most of you have answered that. That's well done. So let's move to the second part, second question. So how do we resolve the issue of not knowing the standard deviation, right? So standard deviation sigma is not known. What do? You, instead of that sigma part, you're going to bring in a concept that is called as S. So S by root n is what we use. So that means you are going to use the standard error. S by root n is nothing but the standard error, right? Yes, most of you have answered that. That's very well done. Let's move to the next question. Okay, so what are the various factors not needed to find the sample size? N is the question. Okay, I'm supposed to find out N, right? N equation you try to remember, right? In that, do you have the confidence level? Yes. So that's actually the percentage, like 0.95, 0.99, whatever you write there, that's the. Then true value of the mean or the fraction, right? That needs to be estimated, right? So we'll come back to that later. So let's look at the next one. Required error margin, right? Yes. So E, capital E itself is the error margin. I'll say that I need 1% error, 5% error. So that's the one which is this. And the standard deviation of the quantity being estimated, right? So all the three are needed, which means, right, the exact value of the mean or the fraction is to be estimated. This is not required. So in this case also the B, right, is the, or the second answer is the correct answer. Okay. Okay, so most of you could recall, right, or you could understand, right, the concepts we were discussing so far. So since the, what you call, say the fraction as well as the estimation of the mean, right, by using a distribution is pretty much what you call related, right? Since we dealt the concepts in detail, now you will be able to right, understand, recall, and apply whenever required. Okay, so I'm very sure about that now. So let's move further. Right. So we'll move to the next part, wherein we try to change our question. Right. So far, try to recall the question. Question said that, like, what is the fraction? Right. I am trying to estimate one of the parameters. At the same time, my other question will be, what is the average value of something? So you see, you are trying to find out a specific value, right? You are trying to estimate a value. It can be fraction, it can be mean, like that. But now onwards, there is another, actually, there is another part. That is, that kind of problem also we can try to solve for using the statistics. Statistics deals with actually another set of questions. Answering that is called as a hypothesis testing. So hypothesis testing falls under a category of problem which we try to understand using these examples. So it says, there is a statement saying that the base rate of women faculty in engineering is 10%. Right? So you see, there is already, they have done some calculation and they are giving a statement to it. This is something like true or false. Now, I have no data with me, right? I have to go ahead and do some calculation, right, to say yes or no for this. Possibly. Let's not stick to the yes or no type of, because we are not going to apply the yes or no type of answers over here. Okay. Sorry. At the same time, let's go to the second example. In a 80-member expert panel, right, there's a committee formed where the number of members is equal to 80, right? There were 2 women out of 80, right? So the question is it a confidence? Is it pure coincidence? Is it a coincidence, or there is a willful bias? Right? So you see, right, I have to apply the known facts over here to answer this. It can be a pure coincidence, it can be a willful bias. Somebody purposefully have put only 2 women in a committee of 18 members, right? So in order to answer this, the approach that we are going to use is called as a hypothesis testing, right? Normally, so try to model, I'll try to modify the question, right? So the formal question that normally we ask is of this type. Could this observation, somebody observed something, right? And is it by chance? Okay, nobody did it on purpose, by chance it happened. All right, so this is only one example, right? So other example I already mentioned, the base rate of women faculty in engineering is 10%. Is it because of say somebody did that on purpose, they selected only 10%, right? Is it because of some reason, or it's it happened, right? Right, so that's what, is it a coincidence or is it not? Normally this kind of situation we face, right, and we are supposed to answer that. So almost every time our answer will be either it's just by chance, okay, otherwise it's, right, you may have to say that it is not by chance, right? I will not say that it is somebody has purposefully done that. I'll say that it's not. Our first part will be yes, it is by chance. Second is it is not by chance because of some other reason which we, if those who are interested, they can explore further. So this kind of analysis, right? You see, we are not estimating any of the parameters over here. We are not trying to calculate mean, fraction, or any other, say, standard deviation, variance. No, we are not estimating any of them over here. Okay, so such questions, I hope you understood what kind of problems we are going to face now, right? The solution is, right, actually a 4-step process, right? So you can see here the 4 steps that we are going to follow, right? Again, this takes some time to get adjusted to everything what we're going to learn now. So hypothesis testing is completely different compared to what we were dealing so far. So it will take time, so we'll go slowly, we'll not rush. Okay, so the first part is called as you formulate a hypothesis, right? I have a problem, I'll make 2 statements, I have to select one of them at the end. So first one is the first, whichever you give a preference. Normally it is, you say that it is it's a pure coincidence, something like that, you make a statement. Okay, whatever I observe is a sorry, it's a pure yeah, coincidence, let's say that. Okay, so let's assume that the first statement I'll make, that it is a pure coincidence, you call it as a null hypothesis, okay, which you want to nullify at a later stage. If you want to go to the next part, alternative hypothesis, you have to nullify that. That's why the name is null hypothesis. Okay, so you have to prove that it is not this. That's why I go to the next one, that is the alternative hypothesis, by proving something. So you are saying that I'm nullifying the first hypothesis and I'm going to the next hypothesis. I'm going to select that. Sorry, just one second. Okay, so you are supposed to nullify the null hypothesis to select your next hypothesis. That is called as an alternative hypothesis. If this is not the answer, the other one will be the answer. Okay, so since you are supposed to nullify something, that something is null hypothesis, to go to a next hypothesis, that is an alternative. So the names are given according to this convention, right? So you will formulate 2 statements, you will call it as a hypothesis. Okay, formulate the hypothesis is the first part. Then we need to define what is called as a test statistic. So statistic, already just in the previous slides, one of the slides we have seen that. So like statistic T is equal to something we have formulated. Sorry. So let me just show you that. You see here the statistic T is equal to something. It's not necessary this, we'll be following the, what you call, same statistic. We may or may not apply the specific distribution, but just understand, we will try to write an equation, okay, according to the scenario on which the problem is formed, right? We will be building up one equation, right, corresponding to certain distribution only. Okay, so that part is what we call as a test statistic. Okay, that we are going to test. So it may look like, no, I don't have any data. Somebody said that base rate of women faculty is 10%. How can I do a mathematics on that, right? We'll come to that. As of now, don't worry, just understand. Okay, the procedure you just try to understand. So mathematics will come to that at a later stage, right? So second one is trying to write a statistic. Test the statistic is a technical term used here, which means you are trying to write some sort of equation that is based on some standard distribution only. Okay, we'll come to that. Then using that, do a mathematics and calculate a p-value. This could be something similar to the probability only. Okay, so we call it as a p-value. Then you will compare that with a significance level. Significance level is something like my error. Okay, I said 5% error, 1% error, like that. It's not a confidence, it's on the other side. There is a significance level. We'll discuss everything in detail, but I'm just giving you a hint what and all we are going to follow to perform what is called as a hypothesis testing. So normally we have a statement given, right? That's my problem. Corresponding to that particular statement, I will form two. I can convert that into, say, two more statements. One I call as a null hypothesis, right? I have to mathematically prove that this is not true, so I go to the next one. So I nullify my first statement. I go to the alternative statement. I select alternative statement as my answer, let us say. Okay, so that is what is going to happen, right? To do that, we'll do the mathematics. We'll bring an equation, test the statistics, solve that, get a p-value, compare the p-value with something called as a significance level, right? So depending on a condition, you will either reject or accept the null hypothesis. Accept the null hypothesis means you say that if at all you have chosen that, yes, this happened, this is a pure coincidence. If at all you made the null hypothesis like that, right? That means you accept that. Say you are accepting that, yes, this is pure coincidence. At the same time, you didn't significance level. You actually didn't satisfy that whatever condition is required over there. Then you reject that, which means you say that it is not a coincidence. Something right happened. Somebody has done this on purpose. All right. So normally this will be the process. Significance level, something like a threshold. I'll come to that. Okay. So significance level is something related to the error, 5%. Like previously we were solving with the 95% confidence, 99% confidence. Now we have a significance level, something related to the error with 5% error, 1% error, something like that. Okay. Just try to relate that as of now. I'll come to the exact topic at a later stage. Okay. So this will be the procedure, the standard procedure, or the steps we need to follow to do this. Okay, so now I'll go in detail, right? So let's look at the concepts slightly in a detailed fashion before we actually apply this to certain problem and we'll solve. We'll look at the steps. So as you can see here, the step number 1 says formulate the hypothesis, right? So formulate the hypothesis suggests that you need to have two different statements, right? So corresponding to any given problem, the step number 1 says, right, possible hypothesis. One denote, it's again one of the notation we find in textbooks or the reference is H for the hypothesis. So H naught, so null is 0, so H0 is the common notation for the null hypothesis. Again, it's just a convention. Okay, you can change anything as per your preference. So the null hypothesis denoted by H naught, this says that whatever you have observed, right? So there is a maybe the example says that panel chosen contains only like this many number of female candidates, right? You say that observation is a result of chance. Okay, nobody did that on purpose, right? If I reject this, I should have another alternative answer over there. So that is what is called as the alternative hypothesis. Okay, so these are the conventions that we are going to follow. Right? H naught denotes the null hypothesis. At the same time, if I have HA, or some of the authors or some of the references will write it as alpha, H alpha, no problem. Okay, it's alternative, right? So you see, again, this is what corresponding to the example we were discussing so far. We can try to write something like this. The alternative hypothesis is something like whatever you observed so far, right, result of a real effect. Okay, right? Real effect in the sense it's not a pure chance, right? Right? It's somebody has done something. So that's what I call it as a real effect, right? Plus some variation, right? So that variance is there. As of now, if difficult to understand, just leave that second part. Okay, variation part just leave. Remember, somebody has done that on purpose is the point, right? So you see the explanation right below. So see that what is H naught? Panel was randomly chosen, right, from the population with the P equal to 0.1, because the previously it said that 10% something, correct? So 10% whatever we told, right? Because of the 10%, you have chosen just 2 out of 8, maybe, right? At the same time, that is a null hypothesis we formed. The second one, right, the alternative hypothesis could be something like this, right? So that is women are less likely to be in the panel than their base rate, right? So that means it is P less than 0.1, correct? So base rate is 10% means normally you will find it 10% in 10% women in the country with slight variation. That's okay. Okay, so P is a probability. All right. Yeah, sure. So I have to make 2 statements. Again, this is just an example. Okay, it's not necessarily the same thing to be formulated. I'm trying to give an explanation what we are going to do in step 1. Right. So step 1 means I have to formulate 2 statements from the given question. Right. So in this case, one is called as H naught null hypothesis, H alpha, or HA, which is the alternative hypothesis. So one possible H naught and H alpha, one set is something like this. So you look at the question. Sorry, look at the question. Look at the statement example. Normally, right, in engineering, women faculty will be 10%. So 10% means what? Out of 80%, 80 member in a group, 10% means 8, right? Close to 8. Sorry, I'm talking since early morning, so my voice is just give me 1 second. Yeah, sorry about that. So totally, if you form a group of 80 members, and we say that generally the tendency is that 10% of them is expected to be women. Okay, so that means you expect 10% of 80. That is 8. Close to 8. 6, 9, something like that. But you see, in a 80-member group, right, it says that there are 2 women. So we are formulating 2 things, 2 statements corresponding to this. First one is that it is just by chance. Okay, nobody has done this on purpose. So that is the H naught. Okay, second one, somebody did this on purpose. Only 2 things we are trying to write, but I'll bring because they have mentioned some 10%, etc. in the statement, right? So what we are trying to do here, we are bringing the probability also in the statement itself, because I don't have any other data with me. I have to use this somehow to do the maths at a later stage, right? So see the statement. Panel has randomly been chosen with the from the available population. Population can be there may be 200 faculties, 2000 faculties, right? Out of which 80 were chosen at random. Ladies or the female faculties randomly chosen, which came to be 2. So you see that panel was randomly chosen from the population, right? So it means it is nobody has done this on purpose. So that's what is the meaning. Okay, panel was randomly chosen from the population with the p is equal to 0.1. Probability is 10%. Okay, that's all. So this means what? Nobody has done this on purpose. It's chance. Okay, the second one, it means, right, women are less likely to be in the panel, right? Lesser than their base rate. Normally you find 10%, but now you see I am finding it lesser than 10%. That's what I am making as my second statement. Which means, right, what's the meaning of this? Somebody should have done this, right? On purpose, because there is 10% available, women available always. Okay, so I hope this point is clear now. I didn't notice who asked that question. I think, yeah, Upkar. Yeah. Yes. Okay, that's correct. That's correct. So normally, whatever happens, you look at the statement once again, right? So look at the statement. Statement says, in general, right, 10% are women. Okay. Whenever you form a group or whenever you go to a engineering institute, let's say 10% are women. That means the same 10% should come into any group you form, correct? Because you randomly pick. Right, but what happened? They tried to form a 80-member committee in which only 2 are women. That means what? It's less than 10%, correct? 10% of 80 is, right? How much? 8. At least close to 8 it should be there, like 6, 9, 10, whatever. Right. Now, the question is it a coincidence or is it a willful bias? So you see that the example, whatever we have written over there, right, is a question for. We are trying to solve this. We are trying to say the answer, right? But before that, my step number 1 is formulate the hypothesis. I need 2 statements. So the H0 says it is purely coincidence. But I don't write it's purely coincidence. I bring the probability given over there. So panel was randomly chosen with the P equal to 10% and we got this answer. So nobody has done anything direct. It's a random thing. That's what is H0. Right? You always need 2 statements. First statement is this purely coincidence. I write it in a different fashion. So the second part says that it is not it's not pure chance. Somebody has done. Somebody has done, that means what? Normally it is 10%, but purposefully somebody has done this less than 10%. So you see the second statement. Women are less likely to be in the panel. Okay, so in a institute, yes, there are 10%, but when a committee was made or a panel was chosen, women are less likely to be present in that particular committee, that particular what you call panel. So lesser than the normal rate. What is the normal rate? Normal rate is 10%. So you have the value less than 10%. So that's what is the meaning. Okay, I hope that is clear. Sure. So let's move further. Now, this is the step number 2. Right. So you see, women present, women not present. Again, this is the example corresponding to this given problem. Okay. We may have to formulate in a different fashion. We may have to bring a different random variable into picture. But right now, you see, I'm trying to relate the maths for this. Okay, I'm trying to do the maths for this. That is, identify what distribution can be set or can be used for this, what type of randomness you are going to have here. So being selected or not being selected, this means true or false kind of situation here. So the one best suitable random variable is the binomial. You can use the binomial distribution. Okay, so recall the problems we solved, right? In one of the classes, what is the chance of selecting 2 people out of 80? Right? Are you able to recall that? Probability of selecting so many number of candidates out of so many number of candidates, right? Selection of, so there is in a class there are 5 girls, 6 boys. A group is formed, right, of say 6 students. What is the chance that there are 2 girls, 3 boys? Okay, so this kind of problem. Yes, go, right? So, right, binomial is chosen when you have, right, 2 possibilities. Head, tail, true, false. It will rain today, it will not rain today, like that. Okay, so try to recall. I'll give say 10 seconds to you to understand this, right? So test statistic needs to be defined. You need to choose that. So whatever various distributions we are familiar with, out of them you need to choose one that suits to the problem which you are trying to solve. In this case, women getting selected or not selected. Okay, so we define the test statistics. Okay, identify a statistic, in the sense identify a distribution, right, which can be used over here. Okay, so probability P is given and also the total size is given, which is n equal to 8. Okay, all right, is that fine? Any doubt? Okay, look at only step number 2. We'll move to the step number 3 after this, after I clear if you have any doubt. Okay, so no doubts? That's fine. So let's move to the step number 3. We calculate a probability value that is denoted by P. Okay, now let us say there are 2 hypotheses, 2 statements made, and we denoted H0 and HA. Right. If at all, the first statement denoted by H0, which we call as a null hypothesis, if at all that is true, right, look at the condition. If I'm saying that, okay, the null hypothesis is true, right, when I'm supposed to calculate a probability. Just now we have chosen a binomial, and so what is the probability of observing a test statistic at least as extreme as one we observe? That should be the extreme case, right? So I'll explain this further. So this is the point which the reference is. Okay, so null hypothesis is true whenever whatever I observe means what, right? This the women candidates being selected is lesser than 0. Okay, so whatever I observe is an extreme case, right? So extreme, how do you identify that's the extreme? There has to be some threshold, correct? So we'll come to that. So if at all that is the case, you will say that, right, it is the null hypothesis, which we made a statement that this is pure chance. Okay, so if the value of P0 is smaller, right, sorry, if the value of P, whatever probability we calculate, if it is smaller, then, right, it means the H0 is true. Probability is less means what? Very less chance means what? Whatever we are seeing, the chance of that is very less, means it's just a chance. There is a normally probability means what? What is the chance of raining today? You will say 10%. There is a chance of 10% means what? If it rains, though the chance of raining is 10% and it rains today, means it's a chance. But if you get a value which is right, which is bigger, right, like 90% chance of rain, right? So that is not by chance. Okay, that's something which is going to happen. So in this case, somebody has done. Okay, so are you able to relate that way? So we have to calculate a p-value now. So how do you do the p-value, right? So use the same notation. Okay, so I'm not doing the mathematics right now because we already have solved a lot of problems, right? On binomial random variable. Try to recall. So what is the, how do you calculate that? How do you calculate the this particular value? It's a binomial, right? So NCX p to the power x, right? 1 minus p to the power n minus x. So 80 is n, p is equal to 0.1, x is equal to lesser than or equal to 2 because x is less than 2 because lesser than, now I get an extreme case. Selecting 2 women is the extreme case, not more than 2 should be there. So in order to say that it is pure chance, I have to calculate extreme possibility. So 2 has been chosen. Whatever I am observing here is the extreme case. So what is that? It means you may choose no women, you may choose 1 woman, you may choose 2 women maximum. That's the extreme. That's what is the meaning of the above sentence. I told I'll come to that later, right? So now you understand. So I am supposed to calculate the probability that the chance of choosing a woman, that is x, lesser than or equal to 2, right? So if you want to do the math, right, I'll show you, right? So let's do the math. Anyway, we have just 10 minutes time, so let's use that. Then I'll go to step number 4 and we'll try to wind up over there. Okay, so let's do one thing. Let's do the math. Okay, so this is what I mean, right? So let's say in a given problem, we have n equal to 80. Out of 80, I'm supposed to choose 2, right? And 2 is maximum, right? So probability is given. Probability is generally 10%. That is 0.1. Right. Now I want, what is the probability that the random variable x takes a value lesser than or equal to 2? Why 2? Because when I observed a committee being formed, there are only 2 out of 80. So, right, less than or equal to 2 is equal to, remember, I used to write the same way. So, probability that the x being equal to 0 plus probability that x being equal to 1 plus probability that x being equal to 2. This is what we are supposed to calculate. Since I have chosen the binomial, I should apply the equation. So remember, I told that you need to remember the equations because every time when you solve, you don't get an equation readily. Okay, so that's why I suggested try to remember each of the distribution and the corresponding equation of that distribution, the mean of that distribution, and the variance. These 3 things you need to remember. Okay. In variety of situations will come wherein you need to just recall and substitute those values. Okay, so let's write that. So n is equal to 80. So the first part, it is equal to 80 C 0. So 0 0.1 to the power 0, 0 0.9, right, to the power, right, n minus x. So that is 80 plus, right, 80 C1, 0 0.1 to the 1, 0 0.9 to the power 17. Okay, plus 80 C2, 0 0.1 square, 0 0.978. So this is what I want you to calculate. Okay, so please do the calculation and put the answer in the chat box. So we are expecting a very small value. right? Anybody? What's this answer? No problem. It takes some time. Okay. We'll give maybe 1 or 2 minutes. Zero point 0.01089. Okay. Other answer is 0.0000. I think that is too less. Somesh, can you try again? Others, please try, because the answer that I'm expecting is slightly different than both of these answers. Okay, so please try. Okay, others, please put your answers. Please do the maths. Equation is already given there, right? Just do the maths, so add them up and give me an answer. Okay. Okay. I expect you to uh, verify this answer. Okay, because when I solved, I'll show you the answer I'm getting. Okay, so that itself has been pasted in the PPT. So you see the value which uh, normally we get is 0.00852. Okay, others, please verify this once again. Okay, uh, so this is the probability. We call it as a p value. Okay, corresponding to the given data, right? we calculate a p-value, we fit what you call as a distribution, and for that distribution take this situation, whatever we observed as a most extreme case. Extreme in the sense, getting 2 women is the highest possible case, let us say. That means I may get no women, 1 woman, or 2 women. Take that, find the probability using a distribution. Call that as a p-value. In this case, that comes to be 0.00852. Okay. So in this particular situation, right, what happens? I just have to, in order to decide whether I'm supposed to accept or reject the null hypothesis, see, this is the scenario, this is the condition. If this p-value becomes lesser and lesser, right, then it is against the H0, right? It is not going to be the null hypothesis. You have to reject that. Okay, so let's see what's going to happen in the step number 4. Calculation of P is there till step number 3. Try to access the evidence, right? What do you mean by the accessing the evidence? You will have to use what is called as a significance level. You will decide, because significance level stands for what is the chance of error. Like previously we used to choose that, right? 95% confidence, 99% confidence. So corresponding to a confidence level, you can even write the opposite, correct? 1 minus confidence is the alpha, right? Do you remember? So that is what we are trying to use now. So what are the standard values? I told we need to move away from 0.5, go closer and go far away. So when I move far away, I will be using 95% confidence corresponds to the alpha value 0.05. When you use 99% confidence, the right alpha value will be 0.01. That's why the alpha is standard, right? The recommendation is that you have to use 0.05 or 0.01. And when I choose such a case, I am supposed to do this comparison. Whatever probability you calculated now, right? Compare that with the alpha, right? Whatever alpha you choose, you are left, it's left to you. Depending upon what is your preference, you can choose that. If at all this p-value obtained is lesser than alpha, then you say that I am ruling out the hypothesis, null hypothesis. H0 is not true. The other one is true. I reject the H0, right? Right. So that means in this case, compare. 0.008 is less than 0.01. That's why I actually, my answer will change if I take Ruchi's answer, saying that 0.01, this is more than that, right? So that's why I asked just to verify. Okay, once again, this means, what is this, right? Here the condition is satisfied, and that means null hypothesis, whatever I formed, is not true. Which means what, right? It is not by chance. Yeah, so you're getting same answer, Ruchi? Yeah, okay, 0.0085. Fine. So that means, right, this condition, right, is satisfied. It is lesser than or equal to alpha, means it is not a null hypothesis, it is the other case. So what is the other case? What is the alternative hypothesis I formed there, right? Normally, women, so in an institute, you find 10% women. But on purpose, when I formed a group of 80 people, we chose lesser than 10%. That was on purpose. That's why I wrote here, something is fishy. Somebody has done that. Right? So the question was, right? Let me go back to the question. Now you see you are able to answer that question form. Yeah, here. So the question was, I observed this thing, right? First 2 points are what have been observed. Now the question is it coincidence or is it a bias? You see, by fitting a distribution from the observed data, now you are able to answer. You are able to answer that. Okay, so your answer is yes, somebody has done that. It is not coincidence, right? So applying this particular procedure and right, trying to answer right such question is what we call as the hypothesis testing. Very important. Okay, so last slide of the day. What are the various types, right? So large sample significance test. That means estimating the fraction and identifying, right, if it meets certain requirement. We'll be dealing this in a detailed fashion, but just remember these names. Okay, first one is large sample significance, right? So you are trying to estimate a fraction and determining whether that fraction you calculated meets certain requirements or not. The second and the third, right, is pretty much similar. Large sample mean test, right? Estimating the mean, right? Again, after estimating something, you will determine that, okay, whether your conditions are met or not. So that is large. For a large sample. The third one is small sample, right? I don't have a large sample. We'll be dealing with a very small sample. Still, I'm trying to estimate the mean value and determining whether the estimate value meets your requirements or not. So first one is basically estimating fraction. Second and third deal with the estimation of the mean values. So second one for large data set, third one for a small data set, small sample. Okay, so that brings to the end of the session, right? So please feel free to ask if you have any question related to this. Okay, so looks like everything is fine. Any question? Yes, Somish. No question? All right, all right. Yes, Mon. Calculator. Yes. Okay. So such calculations cannot be done in any other fashion. So if you want a quick answer, suggested to go with a calculator. Okay. Yes. All right. So that brings to the end of this week's class. I hope this is useful. I appreciate your effort in engaging this class, and I also appreciate your patience listening to the session. Okay. So we'll meet in the upcoming week. All right. So till then, take care and have a great time.